Aloha BIOCHEM. This video begins Chapter 4 on covalent compounds, and we introduce covalent bonding and Lewis structures. We're starting a new chapter now on covalent compounds. You can see in the picture some extra strength Tylenol. This pain reliever contains the active ingredient drug called acetaminophen. Acetaminophen is a covalent compound, and its molecules have an interesting structure, which you can see right here. This is an example of a skeletal representation of a molecule, and later in the chapter we'll discuss such structures and we'll talk about what all these lines and such represent. But for now, in this video, we will give a brief overview of the chapter, and we'll get into covalent bonding and Lewis structures of simpler molecules, and touch on some of the other concepts as well. In the previous chapter, we covered ionic compounds. This time we'll do covalent compounds. These two are the two main categories of compound substances. Let's recall that a compound is a substance formed from two or more elements combined in fixed proportions. Fixed proportions means the substance has a chemical formula which describes the proportions of the elements in it. For example, the substance water has the chemical formula H2O. For every 2 hydrogens, there is 1 oxygen. So the proportions of atoms in water are twice as many hydrogens versus oxygens. And each substance has a chemical formula. Now, ionic compounds are made of ions, and there are always 2 types of ions. You have your positive cations and your negative anions. The cations are positive because they are missing electrons. They have lost electrons somehow, and so they're positive in charge. And the negative anions have extra electrons, so they have gained electrons somehow, and that makes them negative. And those opposite charged ions attract each other, and that force of attraction is called ionic bonding. Ionic bonding is what holds the compound substance together. Ionic compounds are made of metals and nonmetals, and some examples are sodium chloride, magnesium iodide, potassium nitrate. The metals are the positive cations and the nonmetals the negative anions. You can see one of those polyatomic anions here, nitrate. Covalent compounds, on the other hand, are made of molecules. There are no ions in covalent compounds. A molecule is a group of atoms that are attached together by the sharing of electrons. And that sharing of electrons is called covalent bonding. When you have 2 atoms that are sharing a pair of electrons, they're both hanging on to the same pair of electrons, then those 2 atoms are bonded together. And so covalent bonding is different. You have 2 atoms holding on to the same pair of electrons, and ionic bonding is, electrons have left one of the atoms and went all the way over to the other one. So one atom has now missing an electron, it's a positive cation, and the other one has an extra electron, it's a negative anion, and so that opposite charge attracts each other. That's ionic bonding. Covalent bonding is the sharing of electrons. Covalent compounds are made of nonmetals only, and some examples are CH4, methane, NH3, ammonia, and H2O, water. Now, whether we're discussing the ionic bonding or the covalent bonding and compounds, the bonding principle governs both types. And this principle states that when bonding, atoms gain, lose, or share electrons in order to achieve a filled outer valence shell. In the last chapter, we discussed how atoms gain and lose electrons to become ions, and in doing that, what they are doing is they're trying to achieve a filled outer valence shell. They're trying to become like noble gas atoms, because noble gas atoms have filled valence shells. So let's quickly recall sodium chloride and how it does this. Sodium chloride is made of the elements sodium and chlorine in a 1-to-1 proportion. And sodium is element number 11. If it just loses one of its 11 electrons, then it will have 10, like the noble gas neon. And neon has a filled valence shell. All of the noble gases have filled valence shells. So sodium loses one electron to become a +1 ion, and that makes it like the noble gas neon with its filled valence shell. And chlorine, on the other hand, is element 17, and all it needs to do is gain one electron to have 18 like the noble gas argon, and then it will have a filled valence shell like that noble gas. And so sodium loses one electron, chlorine gains that electron, and that way both of them now have a filled valence shell, the two ions do, and that, you know, is the bonding principle at work in ionic bonding. The covalent bonding that attaches atoms and molecules also is governed by the bonding principle, but here the atoms are not transferring electrons from one to the other. They're both sharing pairs of electrons between them. And so by sharing electrons, atoms are able to achieve filled outer valence shells as well. They just go about it a different way. And we'll discuss this in a little more detail in this chapter. We touched on it in the last chapter, but we're going to go into more detail now. So in this chapter, we are interested in covalent bonding and molecules. Now, there is a primary goal in this chapter, and if you were able to achieve this goal, then you have a pretty good handle on the material in the whole chapter. So here's the goal. If you're given a chemical formula of a covalent compound, you should be able to write the Lewis dot structure of the molecule, determine the three-dimensional shape of the molecule, and also determine whether or not the molecule is polar. And don't forget to name it. You should be able to name covalent compounds. Now the first part, determining the Lewis dot structure of the molecule, these things tell us how the atoms are connected together and what the bonding looks like between the atoms. This is going to be the largest step to achieving this goal. So most of the work goes into this step, and I am going to outline a good method for getting the Lewis structure of a molecule. Once you have the Lewis structure, it's a pretty straightforward procedure to assign the three-dimensional shape. You see, the Lewis structure just tells you how the atoms are connected. It doesn't really tell you which way they are pointing. And so once you know how the atoms are connected, you then want to determine the three-dimensional shape of the molecule. And to help with that, we will be using table 4.2 in the textbook. And here's what table 4.2 looks like. So we'll discuss this table in more detail as we go through some examples. And after you have the three-dimensional shape of the molecule, you can then determine whether or not the molecule is polar. Is it polar or nonpolar? Polarity describes whether or not the molecule has a positive side or a negative side. Sometimes more electrons collect on one side of the molecule versus the other side. And so when that happens, you know, the side with more electrons is kind of more negative in charge, and the other side with less electrons is more positive in charge. And so we say the molecule is polar. And many molecules are polar and many are nonpolar. And so once you've achieved the first two steps, it'll be pretty easy to determine whether or not it's polar. And to do that, we're going to use figure 4.4. And I'll show you figure 4.4. This is a table of electronegativities. And electronegativities describe atoms' ability to pull electrons towards their end of a bond. So if you have, say, fluorine attached to carbon, fluorine has a greater electronegativity and it will pull electrons away from the carbon. And so that will help the molecule become polar. So we'll be using this figure to determine the polarity of molecules. Now finally, you need to be able to name the molecule, and you can actually do this first if you want. So name the molecule and then do the structure if you want. To name the molecule, we're going to use the help of table 4.1. And I'll show you table 4.1. Here it is. It lists the common prefixes of nomenclature. And so we'll be using this table to name covalent compounds. So there you go. It's a pretty straightforward goal. Given a chemical formula, draw the Lewis structure, determine the shape, determine the polarity, and name it. Now, along with this goal, we're also going to throw in some goodies. We'll discuss resonance structures and isomers and skeletal structures like that one that we saw for acetaminophen right there. All right, so the first step in achieving the goal is to get the Lewis structure, and I'm going to help you do that. Here's a good method for drawing Lewis structures. Okay, how to draw the Lewis structures of molecules. So you need to be given a chemical formula, and suppose we're given the chemical formula HCl. HCl. So there is our formula. You have one hydrogen and one chlorine. Now, to get to the Lewis structure, you're going to follow these three steps. In the first step, you draw the dot structures for each atom in the formula. You have one hydrogen and one chlorine, so draw the dot structure for a hydrogen and draw the dot structure for a chlorine. Hydrogen gets 1 dot and chlorine gets 7 dots, and that's because hydrogen has 1 valence electron and chlorine has 7. I'll remind you that the periodic table tells you how many valence electrons atoms have. Hydrogen is in group 1a, and all of the atoms in group 1a have 1 valence electron, and so they get 1 dot. Chlorine is one of the halogens in group 7a, and so chlorine gets 7 dots. So here are the two dot structures for the atoms. Now, after you've done that, the next step is to position the atoms next to each other, matching up any unpaired electrons. So you see this unpaired electron on the hydrogen and that one on the chlorine. Electrons like to pair up, and so this electron is looking for another one to pair up with. And so what we're going to do is we're going to move these two atoms next to each other. These are kind of like puzzle pieces, and you need to fit these pieces together properly in order to complete the puzzle. So you move the chlorine and the hydrogen close to each other, and you match up any unpaired electrons. So you can think of rotating, all of these valence electrons so that this one is now matched up with hydrogen, and there you go. Now later on in the chapter, we'll see that with more complicated formulas, when you have maybe 4 or 5 atoms, there could be multiple ways of positioning the atoms next to each other. Okay? And we'll discuss such situations. So sometimes there's more than one way to do this, and so we say that there are several isomers of the formula. But when you're just dealing with 2 atoms, there's only one way to do it. They have to go next to each other. Okay, when you got 5 or 6 atoms, then there's multiple ways. Maybe one of them goes in the middle in one isomer, and then another one goes in the middle in another isomer surrounded by the other ones, and so that's for more complex formulas, and we'll discuss that later. So after achieving step 2, the atoms are now next to each other. So these two are where the bond is going to go. And that's what you do in step 3. You now connect the unpaired electrons to form the covalent bond. So these two electrons right here, they are going to pair up, and that's the covalent bond. And now hydrogen is sharing that pair of electrons, and chlorine is also sharing that pair of electrons. And since they are both sharing the same pair, those atoms are linked. They're both holding on to that same pair of electrons. Now let's just recall the bonding principle for a second. You remember atoms like to share electrons in order to achieve a filled valence shell. You see, before it did this, hydrogen only had 1 electron, but now it has 2. And that makes it like the noble gas helium with 2 electrons. Helium has a filled first valence shell, okay? And likewise, chlorine, before it only had 7 valence electrons, and by forming the bond, now it has 8. It has what's called an octet. Chlorine now has a filled shell as well. And here's chlorine. You know, with 1 more electron, it becomes like the noble gas argon. And so by sharing that pair, you know, it's kind of like it got another one, and that, you know, is the bonding principle at work here in this molecule. So covalent bonds are often represented by lines. So you can do it like this. This is the old school method, or that's how people usually do it today. So there you go. That's the Lewis structure for HCl. Now, step 3 is usually a little more complicated than the first 2 steps, and when you're dealing with more complex formulas with 4 and 5 atoms, you might need a little bit of help. So you can use as a guide what's called the common bonding patterns and the Octet Rule as well, and these will help you correctly connect all of the bonds between the atoms. Okay, so sometimes this step is a little hard to do, and so you have these tools that can help you. And later on, for more complex molecules, we'll see that there are sometimes multiple ways of bonding all the atoms together. And so we would say that there are more than 1 resonance structures for the molecule. Resonance structures are different than isomers. Isomers are different ways that you can bring the atoms next to each other. So they're different atomic arrangements, okay? Different ways for the atoms to be next to each other. But what resonance structures are there different, you know, ways to actually bond the electrons in a structure. So you might have multiple isomers, and each isomer could have multiple resonance structures associated with it. Okay, and we'll discuss resonance structures later. But this is a simple formula, and so getting its Lewis structure was not too hard. Now, once you get the Lewis structure, if you want to complete the goal, you will then assign the shape, determine the polarity, and name it. The shape of this molecule is trivial because there are just 2 atoms, and as any 2 points form a line, any 2 atoms form a linear molecule. I'll show you here a model of HCl. So you can see the ball and stick model, and this is a linear molecule. When you get to more complex molecules with 4, 5, and 6 atoms, the shapes can become quite complicated, and we'll deal with such cases in our next lecture. But this one is linear. This molecule is also polar. You see, chlorine has the ability to pull this shared pair of electrons a little bit closer towards its end of the molecule. We say that chlorine is more electronegative than the hydrogen atom is. And I'll remind you that that electronegativity table tells us the ability of an atom to pull electrons away from another atom. And here it is. Okay, this table is a table of electronegativities, and each element has a number associated with it. The higher the number, the greater the ability of the atom to pull electrons. And so looking at chlorine, it has an electronegativity of 3, and hydrogen has an electronegativity of 2.1. So that's a difference of 0.9. You know, chlorine has an electronegativity 0.9 greater than that of hydrogen. So it's more electronegative than hydrogen is. And so it will pull these two electrons in the bond a little bit closer towards that side of the molecule. And so we say that this pair of electrons is not equally shared. It's a polar covalent bond. Okay, it's unequally shared. It's kind of like if you have a big brother and you're trying to share the same toy, well, the big brother is going to get the toy most of the time because he's stronger. Okay, so chlorine's like the stronger big brother. So I grew up with 2 big brothers, and so they were both more electronegative than me. Anyway, so yeah, this molecule is polar because of the electronegative chlorine atom. And then finally, let's name the molecule. How do you name it? Well, to name the molecule, you're going to use that table 4.1, which lists the common prefixes. So here it is. And the way you do this is you look at the formula. You have HCl, 1 hydrogen, 1 chlorine. And so you go to the table and you find the prefix for 1, and it's mono. You know, 2 is di, 3 is triad, etc. But here, both of the elements, there are just one of them. And so the prefix is mono. And the way you name it is you have 1 hydrogen, so that's monohydrogen, and then monochlorine. And then whenever you have the first element in the formula, if there's only one of them, you can drop the mono prefix. So we don't say monohydrogen, monochlorine, we just say hydrogen chlorine, or no, hydrogen monochlorine. And then the last element always gets an "ide." So hydrogen monochloride. So it's not monohydrogen monochloride. You drop that mono prefix if there's one in the first one in the formula. And so it's just hydrogen monochloride. That's the systematic name. A lot of people just call this hydrogen chloride because there's only one chemical formula between hydrogen and chlorine. So, but the systematic name is hydrogen monochloride. So there you go. We've achieved the goal for this formula. Got the Lewis structure, the shape, the polarity, and the name. Now, more complex formulas, we often need a little bit of help. We use as a guide the common bonding patterns and the Octet Rule. So let's discuss the common bonding patterns. Now also, when you're doing Lewis structures, you don't want to think too hard about how to draw the dot structures for each atom. You should know how to do that as well. And the dot structures you can get pretty much right from the periodic table. I'll remind you that the periodic table tells you how many dots the elements get. Those in group 1A get 1 dot, 2A gets 2 dots. You skip over these B columns. Those are metals anyway. We don't care about metals in covalent compounds. Group 3A gets 3 dots, 4 dots, 5 dots, etc. And so I've kind of drawn a dot structure representation of the periodic table, skipping over those D block B columns. So here you go, 1A, they all have 1 valence electron, so 1 dot, 2 dots. Boron column is 3 dots, 4, 5, 6, 7, and 8, except for helium. Helium, it only has 2 electrons, but since it's a filled first valence shell, those 2 electrons are paired up, and so it's kind of like noble gases, so it goes in the noble gas column even though it's in group 8A. Now the good news is we only need to think about the nonmetals and covalent compounds. And so even out of them, you're really mostly interested in the elements hydrogen, carbon, nitrogen, and oxygen. So they make up 96% of the human body. And if you master these four, you're doing pretty good, but sometimes we'll do dot structures. We'll draw molecules for compounds containing the halogens, sometimes sulfur and phosphorus as well. I've included here, by the way, the metalloids. So covalent bonding occurs between metalloid elements like silicon and germanium as well. And so, you know, they're not nonmetals, they're metalloids, but, you know, I've drawn them in blue because they do covalently bond sometimes. But master hydrogen, carbon, nitrogen, and oxygen, and also some of the other ones. The dot structures will help you do step one for getting the Lewis structure. Okay, and then once you get to step three, where after you've positioned the atoms next to each other, once you're ready to start bonding the atoms together, you want to know what the common bonding patterns are. You see, the atoms, these dot structures, they're simply the pieces that assemble together to form the molecule. Okay? So you need the help of the common bonding patterns and also the octet rule. The common bonding patterns go like this. Hydrogen has one unpaired electron, and so it's going to want to form one bond. You see, this bond is going to be a shared pair of electrons. So after hydrogen, you know, is going to match this one up with another one to form a shared pair, it's now like the noble gas helium. So hydrogen wants to be like helium, okay? It wants to form that duet. Hydrogen's an exception to the octet rule, okay? It likes to have two. Now boron, with its 3 unpaired electrons, wants to form 3 bonds, okay? And so boron's also an exception to the octet. There are a couple of exceptions to the octet. So boron likes to form 3 bonds, and so you have 2, 4, 6 electrons total around the boron. Now carbon, nitrogen, oxygen, and the rest of them pretty much will always form an octet. Okay, so carbon with its 4 unpaired electrons wants to form 4 bonds. And you'll see carbon with maybe 4 single bonds. It can have a double bond and 2 singles, okay, or maybe 2 doubles and maybe even a single and a triple. In all of these cases, there are 4 bonds, and each one of them involves an octet. So carbon, you know, if you're looking at this bonding pattern for carbon, you have 2 electrons in this bond, so that's 2, 4, 6, 8. So you have an octet here, and they all have octets. Now, once you get to the nitrogen column, you know, nitrogen only has 3 unpaired electrons, so you're back down to 3 bonds. So 2 of those electrons are already paired up. They're not going to be used to form a bond. So the remaining 3 unpaired electrons are going to be used to bond. And so nitrogen wants to form 3 bonds. It could be 3 singles, or maybe a single and a double, or maybe even a triple. Each one of these involves an octet. Okay, so 2, 4, 6, 8. You know, each bond is 2 electrons, so an octet here, and they all have octets. Oxygen only has 2 unpaired electrons, so now you're down to 2 bonds, so it can be 2 singles or maybe a double. And then fluorines and the other halogens just have 1 unpaired electron, and so it's just going to form 1 bond. And so there you go. Most of the time the atoms are going to form octets, and so that's what the octet rule is. So when you're dealing with more complex molecules, you can use as a guide the common bonding patterns. And basically what that means is in the final Lewis structure, look at your molecule and make sure that the atoms have one of those bonding patterns. So let's look at this simple one right here. you see hydrogen has a single bond, and that's the bonding pattern for hydrogen. And you see chlorine has three paired three non-bonding pairs, and then one bond as well. And so that's the bonding pattern for chlorine. And there you go. That's what it's supposed to do. So if your molecule has a carbon or a nitrogen or an oxygen, just look at the final Lewis structure and make sure that those atoms, take on one of these bonding patterns. Okay, so atoms in the molecule most always have these bonding patterns. So let's finish the video with going through a few examples, just some easy ones this video. We'll do the molecular elements. So no compounds yet. We'll save compounds for the next video. Let's do some molecular elements. So we'll do hydrogen, oxygen, nitrogen, and chlorine. You remember what the molecular elements are elements whose particles are molecules. You see, single hydrogen atoms are unstable, and they like to latch onto other hydrogen atoms to form an H2 molecule. Okay, oxygen atoms do that as well, and there are several molecular elements. I think there are 10 of them altogether. So let's achieve the goal for these formulas. You remember what the goal is. Given a chemical formula, determine the Lewis structure of the molecule, determine the three-dimensional shape of the molecule, tell whether or not it's polar, and then finally name it. Okay, so H2. Now, to get the Lewis structure, you remember you first write the dot structures of the atoms. Hydrogen is in group 1A, and so it has one valence electron. It gets one dot. Okay, so you have two hydrogen atoms, so here they are. So here are the two pieces of the puzzle, and it's our job to put them together to assemble the molecule. And to do that, you have these pieces. You position the hydrogen atoms next to each other, and you match up any unpaired electrons. So these two are now matched up. That's where the bond is going to be. And then the third step is to connect the electrons properly and form the bonds. And so this is pretty easy. You just got these two. They're going to form the bond. And here is the Lewis structure of hydrogen. And so there is just one single covalent bond in the molecule. Okay. Now, we can verify that this is correct because we can check the common bonding patterns. So yeah, hydrogen looks like that. So both of the hydrogens look like that. The one on the left has a single bond, and the one on the right has a single bond. If you ever see a molecule where hydrogen has two bonds, that's incorrect. Okay. Hydrogen only has one bond coming out of it. It can only connect to one other atom. Now, what about the shape of this molecule? Well, again, there are just two atoms, and two atoms are always linear. I'll show you a quick model. Here's a hydrogen molecule, and you can see simple linear structure. Diatomic molecules are always linear. Now, is this molecule polar? Does one of the hydrogens pull the electrons more than the other one? Well, of course not. The molecule would be polar, when the atoms are different from one another. The electrons can be pulled towards one side only when you have different types of atoms. If you have two atoms and they have the same electronegativity, then one is unable to pull the electrons away from the other one. And so the molecule does not have a polarity associated with it. It's non-polar. Now the name of this, you go to the table 4.1. So the subscript is 2 here, and 2 goes along with the prefix di. Okay, so the way we name this is diatomic hydrogen. Okay, the molecular elements have interesting naming schemes. This is how you do it. You have diatomic hydrogen. Other molecular elements like phosphorus comes in the form of P4, so we would call that tetraatomic phosphorus, tetraatomic phosphorus. Now, chemists sometimes like to study monatomic hydrogen, but that's an unstable form for hydrogen to be in. You remember, hydrogen atoms like to latch on to other ones to form H2 molecules. So most of the time, if you're dealing with hydrogen in the lab, it's going to be diatomic hydrogen. Our next example is O2. This is one of the two components of the air that we breathe. About 20% of air is oxygen, and oxygen is a molecular element. It comes in the form of O2 molecules. So let's draw the Lewis structure of the molecule and assign the shape and the polarity and the name. To get the Lewis structure, we start out with the dot structures of the atoms. You have two oxygen atoms, and so here are the two dot structures. Oxygen, I'll remind you, is in column number 6A. Okay, so it has 6 dots. And in the final Lewis structure, it's going to take on one of these two common bonding patterns. It's going to be that one. Okay. So here are the two dot structures for each atom. Next step to get the Lewis structure is to position the atoms close together, matching up any unpaired electrons. And so we bring these two unpaired electrons, we match them up. But what about this one over there and that one over there? Well, we need to match them up as well. We can't just leave them out there, because if we did, if this is going to form the bond right there, then, so right now, this oxygen does not yet have an octet, okay? So it had 6. By matching up only these two, now it has 7. So it doesn't yet have an octet. We need to bring this one and that one to match up as well, to look like that. And now the oxygen has an octet, and this one has an octet as well. Okay, and so both of these are going to bond together, and you're going to get a double covalent bond this time. And so here is the Lewis structure for O2. And you can see that oxygen does take on one of its common bonding patterns. It looks like that. Both of them look like that. Okay, now again, two atoms are linear in a molecule, and so the shape is trivial. They're the same type of atom, and so it's nonpolar again, and we'll call this one diatomic oxygen. The other component of air, about 80% of air, is made of nitrogen, and nitrogen is in the form of N2 molecules. Nitrogen atoms are in column 5A, so here's oxygen in 6A. Nitrogen's in column 5A, so 5 valence electrons this time, 5 dots. And in the final Lewis structure, it's going to look like one of these forms. It's going to be that one with a triple bond. Okay, so here are the two atoms. We bring the atoms close together. We match up unpaired electrons, and if you just try and match up these two, you can't forget about those and those as well. You see, just matching up these two, you don't yet have an octet on the nitrogens. Okay, it had 5. Just matching up these two, now I count 6. Okay, so that's not good enough. So we got to bring this one here. Maybe this one will match up with that one, and maybe this one will come down and match up with that one. And there you go. Now we're ready to form the bond. It looks like the nitrogens will now have an octet, and you can see you're going to get a triple bond this time. And that's the Lewis structure for N2. This molecule is, of course, linear, nonpolar, and we'll call it diatomic nitrogen. Our last example is Cl2. This is chlorine, one of the molecular elements. And chlorine is in group 7A, so just a single unpaired electron. I'll remind you, chlorine, like the rest of the halogens in group 7A, look like this, 7 valence electrons, and their bonding pattern is pretty simple. You have 3 non-bonding pairs, and then 1 bonding pair. So that's what it has to look like. And so you position the atoms next to each other, matching up any unpaired electrons. So you're ready to go. You form the bond, and that's it. So you see both chlorines have an octet. They also take on their bonding pattern that they're supposed to, and it's a single bond. Chlorine is kind of like hydrogen. You know, it likes to form just one bond. Go back to those bonding patterns. You see the halogens like to form one bond, and hydrogen does as well. Now, again, chlorine, 2 atoms is linear. They're the same kind of atom, so it's nonpolar, and this is diatomic chlorine. So these were pretty simple examples. In our next video, we'll discuss more complex formulas, and we'll get into some more interesting shapes. So stay tuned for that. Aloha.